Hello and welcome everyone to our poster session. I'm Sheikha Alkhadhr, a PhD student from Al Makawi Lab in Pennsylvania State University, and I'll be talking about how numerical representations of the skull can affect the intracranial fields in simulation. Neuromodulation is one of the most surprising applications of transcranial focused ultrasound, which in turn requires a great deal of study and simulation for the purpose of development and adjustment. In our work, our drivers are the heavy reliance on transcranial focused ultrasound simulations in research, and how this alone can lead to major modification and breakthroughs in adjusting critical parameters of key skull features in so many experimental and actual setups. The nature of the human skull and its features are very challenging to put in an accurate numerical representation. In addition to that, focal precision and targeting pressure is an ongoing research. In our best effort, we aim to have a clear insight comparing the two numerical representations using CT imaging. We also study the impact of these representations on the intracranial fields to illustrate realistic simulations of a propagating acoustic wave. We used the intensity of the CT images for creating the numerical representation of media, skull, water, and brain tissue. We achieved the acoustic properties from the Hounsfield units. The CT images were of a black African male subject around the age of 13. The images were a part of a de-identified clinical data from the image repository of the Washington University, all part of the pediatric head modeling project. According to the resolution mentioned here, the intensity of the CT image were registered with a head atlas to create a Hounsfield units representation. Two simulations were performed, one that represented a heterogeneous medium with Hounsfield units of the CT image. This leans more towards constructing an actual skull texture, and in the other simulation, the acoustic properties like densities and sound speed of each medium separately, water, skull, or brain tissue, were averaged. This exhibits a simulation environment with more homogeneity. In the acoustic simulation, we have utilized the finite difference time domain method to solve the decoupled form of the acoustic wave equation. The transcranial focused ultrasound simulation looked similar to the illustration of this figure. The 64-element transducer was designed to perform at a frequency of 1 MHz with the shown model details. We discussed modeling wave propagation with the finite difference time domain method in a bit more detail here. The main role of the heterogeneous model of finite difference time domain is to capture the acoustic response of the tissue or medium of propagation. The setup of the simulation grid is as shown here. Taylor series expansion for every node in the grid, and a uniform spacing for both spatial and temporal domains. A perfect matched layer on the boundaries of the grid to simulate an absorbing boundary condition. With all the previous mentioned, we constructed the simulation model with the duration, size, and resolution as shown. Our observation in the focal plane relates normalized pressure on the y-axis to the lateral distance on the x-axis. In the left figure, we saw a drop in the peak pressure that reached 51% of actual simulation, when we only performed averaging of the values in each medium. And on the right side hand, figures show the increasing spread of the focal spot. In summary, as researchers, we realized that indeed skull acoustic properties and numerical representations are important in transcranial focused ultrasound simulations, and the use of values that are more homogeneous in simulations to represent skull acoustic properties has a visible effect on the peak pressure and focal spread, therefore showing effect on the resulting intracranial fields. The projection of this work involves using multiple frequencies and observing how beam steering might affect the skull. We also would like to target globalizing the study to include more diverse set of skull geometries. Thank you.